Another day, and here we are, chapter 14. In chapter 14, we're going to be talking about states of matter. We're going to be concentrating in mainly on fluids. We're going to talk about liquids and gases. Okay? So a fluid is any substance that flows. Liquids and gases are both considered to be fluids. All right? The difference between liquids and gases is that liquids are a compressible fluid, which means there's lots of empty space between the particles, and liquids are incompressible fluids, which means there's not a whole lot of empty space between the particles. Turns out that liquids are actually harder to describe than gases. Gases can be thought of as very, very, very chaotic movement of the particles. Liquids are kind of ordered chaos. Solids are complete order. So they're a little hard. Okay? Now, when we talk about fluids, one of the things that we talk about is the fluid's density. Density, remember, is mass divided by volume. If we're using SI units, density would be in kilograms per meter cubed. Quite often in chemistry, we would use grams per centimeter cubed, and 1 gram per centimeter cubed is the same as 1,000 kilograms per meter cubed. Okay? Now, when we're describing fluids, and gases in particular, we're also going to talk about pressure. Pressure is force divided by area. In physics, the unit of pressure is the Pascal. Okay, PA is the abbreviation for Pascal, or the symbol for Pascal. In chemistry, we usually use atmospheres. 1 atmosphere is equal to 101.3 kilopascals. A single Pascal is a fairly small pressure unit. Now, what causes pressure? Well, remember, pressure is force divided by area, so it's going to be due in the gas phase to collision of particles with the walls of the container, or a gravitational response force. Pressure in gases, of course, is due mainly to collisions. Pressure from liquids is due mainly to a gravitational response force. Atmospheric pressure is the pressure due to the atmosphere sitting above you. Standard atmospheric pressure at sea level is 1 atmosphere, or 101.3 kilopascals. We're here in Tuscaloosa. Our atmospheric pressure on a daily basis is pretty close to 1 atmosphere. You lived in Denver, Colorado, it would be less. Pressure at a depth in a liquid is due to the liquid above the object as well as atmospheric pressure. So the pressure is equal to P0, which is the pressure due to the gas at the surface of the liquid, plus the density of the liquid times gravity times the depth. So let's look at problem 5 on page 384. Okay, let me get the system switched over. So let's look at problem 5. It says a 1 meter diameter vat of liquid is 2 meters deep. The pressure at the bottom of the vat is 1.3 atmospheres. What is the mass of the liquid in the vat? Okay. So I know that the depth is 2 meters. And I know that the pressure is 1.3 atmospheres. Okay? So I want to know, and I know that the diameter is 1 meter. Now, let's look at this problem. Okay, I know there's 101.3 kilopascals for every 1 atmosphere. So 1.3 times 101.3 gives me 131.7 kilopascals. Now I need this in pascals. So there's 1,000 pascals for every 1 kilopascal. So I get a pressure of 1.317 times 10 to the 5 pascals. P equals P0 plus rho, the density, times G times the depth. So 1.317 times 10 to the 5 pascals has to equal the atmospheric pressure at the surface. So it's going to be 1.013 times 10 to the 5 pascals, because atmospheric pressure is 101.3 kilopascals, plus the density. Now it tells us that, it doesn't tell us what the liquid is, so I'm just going to leave density here, times gravity, 9.80 meters per second squared, times the depth, which is 2 meters. Okay, so 1.317 exp5 minus 1.13 exp5, I get 3.040 times 10 to the 4 pascals is equal to the density times 9.80 meters per second squared times 2 meters. So I'm going to divide through by 2 and then divide by 9.8. I get the density to be 1.551, and that's in kilograms per meter cubed. Okay? Now, I've got the density 1.551 kilograms per meter cubed, and that has to equal mass divided by volume. Okay? The volume I can get from the diameter and the height. So it's pi r squared, and r here is, so the volume is equal to pi r squared times d. So pi times 0.500 meters squared times 2 meters. So 0.5 squared times 2 times pi, I get 1.57 meters cubed. So 1.551 kilograms per meter cubed equals m over 1.57 meters cubed. So times, hold on, 1.3, let me check my math here. I may have left a factor of 10 in. 1.317 exp5, oh excuse me, 3.040 exp4 divided by 9.8 divided by 2, 3.04 exp4 divided by 9.8 divided by 2, should have been times 10 to the 5. I said it and I didn't write it. Let me change this up here. So, give ourselves a little room here. 1.551 exp5 times 1.57 gives me a mass of 2.43 times 10 to the 5 kilograms. Okay? So that's problem 5. Now, all points at the same depth in the container experience the same pressure. So if I was to look at any point along the bottom of that tank, it would be experiencing the same pressure. Now, let's talk about a hydraulic lift. When you apply a force to a liquid, the force is translated through the whole liquid. A hydraulic lift works off Pascal's principle. If you apply a pressure to a liquid at one point, it must be translated through the fluid. Okay, so let's look at this picture. If I apply a force at point 1, then that force is translated through the liquid. So I push here, pushes up here. Okay? Now if you think about volume, if I were to push down here, I would push up, it pushes an area here. This has got an area A1, this has got an area A2, and notice there's a height difference H between them. I'm going to shrink this thing down just a sec. Okay, the pressure at point 1 here, pressure at point 2, the pressure at point 1 is due to atmospheric pressure, P0 plus whatever the force is. The pressure at point 2 is equal to atmospheric pressure plus the pressure from the height of the liquid there. Okay, so P0 plus force 1 over A1 has to equal P0 plus force 2 over A2 plus the density times G times the H, the height. Well, we know that pressure P0 is the same in both cases, okay, because the atmospheric pressure is the same. So if we simplify this, we can say the pressure at point 2 equals A2 divided by A1 times the force at point 2 equals A2 over A1, force 1, minus rho times G times H times A2. Okay? So you can figure out what the forces are on the two sides and how they have to compare to each other. Now, the volume of the liquid displaced when one piston is moved down must equal the volume of the liquid displaced when the other one moves up. The volume has to be the same. So I know V1 and V2 have to be equal to each other. V1 equals D1A1, V2 equals D2A2. A2. So I also know that D2 equals A1 over A2 times D1. So D2 will always be smaller than D1, the distance that it moved, because A2 is going to be larger than A1. Okay, let's look at problem 42 on page 385. Okay, we're going to look at problem 42. It says a 70-kilogram student balances a 1,200-kilogram elephant on a hydraulic lift. What is the diameter of the piston the student is standing on? And when a second student joins the first, the piston sinks 35 centimeters. What is the second student's mass? Okay. So, look at the problem. In part A of the problem, we're asked what is the diameter of the piston. Okay? Now, we know that the diameter of the elephant's piston is 2 meters. Okay? And that the student is 70 kilograms and the elephant has a mass of 1,200 kilograms. And it tells us that we've got oil. So we're going to look up the density of oil. Okay, this chapter should have densities listed. The density, come on, density of oil. I want a density table. The density of oil is 900 kilograms per meter cubed. Okay, now let's think about equations. Okay, if we look at equations, we go back to our basic equation here. I know that P0 and P0 is the same, and I know that there is no height. Okay, they were both at the same level. So I'm going to use force 1 over A1 has to equal force 2 over A2. Okay? So I can say that the force from the student over the area for the student, the piston it's standing on, has to equal the force from the elephant over the area of the piston that the elephant was standing on. Well, it's a 70 kilogram student, 70 times 9.8, so the force is 686 newtons, area for the student. The force of the elephant, 11200 times 9.8, 11760 newtons, and it was a 2 meter diameter piston, so the radius is 1 meter, so pi r squared, 1 squared is 1. I have 3.14159 here. Meters squared. So if I flip this up, if I work on this, the area of the student's piston is going to, well, actually, I'm going to do it this way. I'm going to have pi r student squared is equal to pi times 1 squared, because I want my math to be easier. So notice that the pi's and the pi's divide out. So I get r squared student is going to be 1 squared times 686 newtons over 1,160 newtons. So 686 times 1 divided by 11760. So I get r squared to be 0.0583 meters squared. Take the square root of that. R is 0.242 meters. Okay, so that's the radius for the piston, or that's the radius of the piston. The diameter would be 2 times that, 0.242 times 2. So I get 0.484 here. I'm going to write R for the student, 0.242 meters. Okay? Now, part B of the problem asks us that it said when a second student joins the first on the piston sinks 35 centimeters. What is the second student's mass? Okay? I'm going to erase, guys. So, again, I know P0 and P0 are the same. So we have this piston going down 35 centimeters. I need to think about how much this piston is going to go up. So thinking about our equations, we know that D1A1 has to equal D2A2. Now, I know that the distance that this moved was 0.35 meters, and the area is pi times 0.242 squared, and that has to equal D2 times pi times 1 squared. So 0.35, notice that the pi's and pi's divide out. 0.35 times 0.242 squared. Take 1 over that. Well, actually no. 0.35 times 0.242 squared divided by 1 squared says that D2 is 0.020 meters. Well, 0.5 meters. That's how much the elephant is going to go up. So on the elephant side, we've gone up 0.025 meters. Okay, on this side we went down 0.35 meters. So the difference in height, 0.0205 plus 0.35. So the difference in height between the two, okay, here is now 0.3705 meters. Here I have my elephant, wee, wee, wee. And down here I have my 2 boys. Okay, standing on their little thing and him standing on his. Okay? Now, going back up here to our equation, I can say that force 1 over A1 has to equal force 2 over A2 plus rho times G times the height. Now the force 1, that's what I'm looking for because I don't know the mass of the one student. The area is pi times 0.242 meters squared, has to equal the force from the elephant, which was 1200 times 9.8, 11760 newtons, over the area, which is pi times 1 squared, plus the density of the oil, 900 kilograms per meter cubed, times gravity, 9.80 meters per second squared, and the height difference is 0.3705 meters. Okay? So 900 times 9.8 times 0.3705 plus 11760 divided by pi. On this side, I have 7011. That doesn't make sense. Let's see. 11760 divided by pi plus 900 times 9.8 times 0.3705. Okay. No, can't be possible. I'm screwing something up. Oh no, it's not. 11760 divided by pi. Okay. 9.8 times 0.3705 times 900. So I'm getting 3267.8. Let me try it one more time. 9.8 times 900 times 0.3705 and 11760 divided by pi. Okay. 7011 and that's going to be in newtons over meters squared. So it's F1 over pi times 0.242 squared. So if I solve for F1, I get F1 to be 1,290 newtons. And that's the sum of the forces from both guys. So it's force from student 1 plus force from student 2 equals 1,290 newtons. Force from student 2 is going to be 1,290 newtons minus 70 times 9.8, 686 newtons. So that's 604 newtons. And if I want his mass, it's going to be 604 newtons divided by 9.8 meters per second squared. So it's a 61.6 kilogram student. Okay? I know, lots of work. But you just keep going back to your equations and plug and chug. Okay? Now, let's talk buoyancy. Oop. Buoyancy. Buoyancy is a net force upward on an object in a fluid due to the fluid pushing on the object. Force of buoyancy is equal to the density of the fluid times the volume of the fluid that's displaced times gravity. Whether an object sinks or floats depends on the relative density of the objects compared to that of the fluid. So if the density of the object is less than the density of the fluid, it floats. If the density of the object is equal to the density of the fluid, it's neutral buoyancy. And if you put it in a position in the liquid, it'll stay there. If the density of the object is greater than the density of the fluid, the object sinks. So volume displaced is equal to the density of the object times the volume of the object divided by the density of the fluid. Okay? So even though a battleship is made out of metal, steel, it floats because the volume of the object is so great. And it has lots of empty space. As long as the volume of the fluid you need to displace is less than the volume of the object, then the object floats. That's why a steel battleship floats. If we have a box of area A on the bottom, then the minimum height for the side of the boat for it to float is calculated by height minimum equals the mass of the object over the density of the fluid times the surface area. And I left an equal sign out there, guys, I'm sorry. This computer doesn't have an equation editor. Mine does. But there should be an equal sign right here. Okay? Equal sign. Height minimum. Every time I turn around. There should be an equal sign right here, guys. I left it out. I apologize. Okay? And it would be a plug and chug equation. Now, let me see how I'm doing on room on the... Okay, we got time. Let's talk fluid dynamics. Fluid dynamics is the study of the motion of fluids. Okay, depending on what field you're going into, you may have to take a whole class in fluid dynamics. Okay? It all starts with the ideal fluid. An ideal fluid is one that fits the ideal model. The fluid is incompressible, so that means gases aren't going to be an ideal fluid. The fluid is not viscous. That means it has very, very low resistance to flow. And the flow is steady. When the flow is steady, we call it laminar flow. The velocity of the fluid at all points in the fluid is going to be constant, okay? And it's going to move in streamline paths. A streamline is a pathway or a trajectory that a particle of fluid follows. All right, so let's look at a picture. In an ideal fluid, streamlines never cross. So if you were to put dye into a liquid, you would see lines of dye moving through the liquid. You wouldn't see the liquid, well, the dye being dispersed through the moving fluid. Now, looking at this picture, when you see streamlines that are closer together, you have a higher speed. Where streamlines are further apart, you have a lower speed. Okay? And in laminar flow, streamlines should never cross. A bundle of neighboring streamlines is called a flow tube. If a tube changes diameter, one thing that has to be maintained is the volume.